Right, okay. I've actually drawn on the board, well, the beginnings of the explanation of cellulose, okay? But let's first of all get to the polysaccharides essentials, okay? So we're talking about multiple monosaccharide units joined together. Underneath that banner, we can divide them into two subcategories. That is storage polysaccharides and structural polysaccharides. Under the category of storage polysaccharides, really we've got two, starch and glycogen. So starch is the storage polysaccharide in plants, glycogen in animals. I hope I'm just going over ground here. Structural polysaccharides, cellulose and chitin. Okay, now the whole idea of structural polysaccharides is they confer strength, and we'll come on to that later on. But the storage polysaccharides, well, they're all about storage, rather obviously. But what do they have in common? So the first thing, both starch and glycogen involves alpha glucose. Okay, in fact I can do this over here, whereas structural polysaccharides involve beta glucose. Remember what we said last lesson about monosaccharides? Hardly any difference between alpha glucose and beta glucose. What is the difference between alpha glucose and beta glucose? See if we can get a succinct answer here, an unambiguous answer. Go on, Joe, go give it a go.
The OH pair next to oxygen is on the other side of the plane.
Okay, so the OH group is not a pair. Okay, that's a good try. The OH group is what we call it on carbon 1. Okay, and you say it's on the other side of the plane. In alpha glucose it points down, and in beta glucose it points up. Okay, it's that carbon 1 I was looking for to distinguish where we're talking about. Good effort. So for storage polysaccharides, we're looking at alpha glucose only. So let's concentrate on starch first of all. Well, here's the first thing about starch, which is not what we'd expect. Starch is actually a mixture. Can anybody tell me what a mixture is? Chemistry. Now I'm asking, what's the chemistry definition of a mixture? You've got this. And the reason I know you've got this because I asked the other class and they actually could give me the chemistry, well, one of them did. What is a mixture? Because we'll use mixture in sort of everyday language. What's the chemistry definition of a mixture? Go on, Lloyd, you're actually considering it.
More than one atom can't be bound together.
You kind of got the opposite of everything you said, and you're not far off then. Okay, go on, Lydia.
Like when two objects are like mixed but not chemically bonded.
Okay, the key point there is they're not chemically bonded. Since I remember from school, they're not chemically combined together. So two or more molecules not chemically combined together. Okay, so starch is a mixture of two components. One is called amylose, and one is called amylopectin. Okay, so the yes, Lucy.
Sorry, you know that word is cellular. What's the one on the end?
Chitin.
Okay.
It's should I not even tell you what the other option is? The other way of spelling it is a little bit rude. Chitin is the correct word. Okay, CHITIN. I wouldn't worry too much about it now because in fact I've just written exactly the same way. Because it's something we'll look at with storage polysaccharides. This isn't meant to be sort of part of your notes, but I always think this is quite a useful way of getting a context here. So, amylose and amylopectin. So let's deal with amylose first because it's an obvious starting point. Remember both alpha glucose, okay? So they're just repeated alpha glucose molecules joined over and over again. In fact, I can show it quite nicely here. Look, alpha glucose. I've got a glycosidic bond between them. Okay, so we know we've got a condensation reaction. So it's the elimination of water that comes out. And we end up then with, I'll draw it differently, that is this glycosidic bond. Proper term, it's the alpha 1,4 glycosidic bond. And amylose, okay, remember this, one of the molecules which makes up the mixture that is starch. Amylose consists of repeated alpha glucose joined together by alpha 1,4 glycosidic bonds. We could put that times N. So we're just going to get that over and over and over and over again. So I could do that if you like, because that's going to be bonded to another one, and this oxygen here is going to form part of the glycosidic bond to another one. Okay, that's amylose. Okay, it's a long chain of alpha glucose molecules bonded through 1,4 glycosidic bonds only. So the fact that I say only implies what? They go into a amylopectin. So amylose only had 1,4 glycosidic bonds. The implication being?
Amylopectin also has 1,6 glycosidic bonds.
I'm not sure that's actually the implication. The implication is, so there's another type of bond, but you actually looked at it, so yeah, it's actually 1,6 as well. So there's another type of bond. Only 1,4 implies, oh, is there another type of bond? Yes, there is. A 1,6 glycosidic bond. So it's possible for glucose to bond. So this is carbon 6, remember? I've made my life difficult here. I've now got to draw an alpha glucose molecule. Okay, so if I see, again, I'll just make my life easy by orientating these a nice way. I've got an OH group here and an OH group here. Remember, this here, change colour here, this is carbon 6, this is carbon 1 of this molecule. When these two join together, I get a glycosidic bond. That is an alpha 1,6 glycosidic bond. Okay, so what we get differently with amylopectin is we have the same base structure, if you like, as amylose, a whole line of alpha 1,4, a whole line of alpha glucose molecules joined with 1,4 glycosidic bonds. But we also get, from time to time, so these are my alpha glucose 1,4 glycosidic bonds, but we also get from time to time a 1,6 glycosidic bond, and then from that glucose molecule, another 1,4, another 1,4, another 1,4, and another 1,4. So if I just take that out, that bond there, that's a 1,6 bond. All the other ones in blue, those are 1,4 bonds. So I've got, what, about 15 alpha glucose molecules there, and I've got 13 alpha 1,4 glycosidic bonds and 1,6 glycosidic bond. And what that does is it gives us a branch. So the difference between amylose and amylopectin is branched in structure, whereas amylose is not. So we might also have a branch coming off even here. So we end up with a branch structure. And the reason I'm drawing it this way, and I'm doing sort of a kind of a coil structure, because that's the structure that storage polysaccharides have. They have a coiled, compact structure. Great idea, because it's about storage. So we want to keep all that energy storage compact. So the coiled structure confers a compact property then, I suppose, to these storage polysaccharides. We can add more on, we get more branches, but we get the idea. Glycogen and amylopectin are pretty much the same. We find glycogen is more branched. Amylose, no branches, meaning no 1,6 bonds. Amylopectin, some branches, so it has some 1,6 bonds. Glycogen, more branches, means it has more 1,6 bonds. For every branch, there's a single 1,6 glycosidic bond. The reason I stress that, I've said it a few times, I've seen before people state this has been a 1,6 bond, and this, and this, and this, because it's part of the branch. No, it's the point of branching, which is where we see a 1,6 bond. Okay, so we're seeing 1,4 and 1,6 bonds in both amylopectin and in glycogen. Properties of storage, last thing, properties of storage polysaccharides. So I said, first of all, they're coiled or compact. I'm not going to write this. If you look in your notes, it's just one to learn, really. The monosaccharide units, the monomer units, are easily added and removed, which is going to be useful because storage, you want to get them back, those monosaccharides back. Importantly, they are insoluble. Now, the words in your notes, it says they're insoluble, so it has no osmotic effect in cells. Think to the stuff you're doing, Mr. James, on osmosis and water potential. So solute potential is defined as solute potential. It's the change brought about in water potential as a result of the presence of a solute. So when something is dissolved in water, it will cause a change in the water potential. It will lower it. If you've got a molecule which doesn't dissolve, it doesn't change the water potential. So it doesn't affect osmosis. Think of the number of glucose molecules that makes up these storage polysaccharides. Glucose, highly soluble. If we have all those individual glucose molecules dissolved in the cell, the water potential is going to plummet because you've got this massive concentration of glucose, causing water to be drawn in from its surroundings and potential problems. The fact that it's insoluble, fantastic. So in your notes it mentions compact, or coiled or compact, monosaccharides easily added and removed, insoluble, so no osmotic effect in cells, and one more which I can't remember, but I suppose it's not really an issue, it's just something you'll see the name. Okay, yeah, there's another one that you've got to learn with it as well.